Hello, welcome back to the playlist of topics on regression models in statistical machine learning. I am Hemakumar Kasala, and as part of this video, we learn about the details involved in building a multiple regression model and one of the two available methods, namely the stepwise regression method. In this part of the video, we learn about the correct and the incorrect models and the shortcomings of incorrect models. We learn about two model building methods and focus on one of them, namely the stepwise regression method. We learn in detail the various steps involved in arriving at a final model using the stepwise regression method and apply the same using a real-life example. And finally, we touch upon certain cautions and points to remember while deploying the stepwise regression method. Let's get into the video. As part of this lecture, we learn about the model building and correct and incorrect models. We learn about the characteristics, usefulness, and shortcomings between the correct and incorrect models, and an introduction to two model building methods that help in arriving at the desired model. In the previous lecture, for a chosen model, we verified R-square, adjusted R-square, error distribution, and run the model utility test using the F-test to check if the model is useful. But are there alternative models with reduced or more number of predictors or using different set of predictors that satisfy the model utility requirements better than the above one? Let's check that out with another example. Here is another example. This is the sample data of size n equals 19 from protein bars that include the price, calories, protein and fat contents in grams. The aim is to arrive at a model that describes the variation in price y, the independent variable, in terms of the predictor variables calories x1, protein x2 and fat x3. Below is the result of one model that includes all the three predictor variables. Price equals 0.252 plus 0.00125 multiplied by calories plus 0.0485 multiplied by protein plus 0.04444 multiplied by fat. R square value at 74.7% indicates that the regression expression explains 74.7% of the variation in y, which looks acceptable, and adjusted R square at 69.6% does not indicate a steep fall as against the R square value at 74.7%. The F statistic at 14.76 and its p-value almost equal to 0 ascertains that it is a useful model. Here is an alternative model that includes just one predictor variable, that is protein content x2 alone. Price equals 0.607 plus 0.0623 multiplied by protein. R square value at 71.1% indicates that the regression expression explains 71.1% of the variation in y as against 74% in case of the previous model. And adjusted R square at 69.4% does not indicate a steep fall as against the R square value at 71.1%. Additionally, the F statistic at 41.9 and its p-value almost equal to 0 ascertains that this model is also useful. Based on the results, the simpler model with just one predictor variable stands as a preferable choice over the three predictors model, considering simplicity. So the question is, how do we arrive at a final model given there are multiple choices in choosing the set of predictor variables? What we need is a correctly specified model. A correctly specified model is a model with all the relevant predictors with transformations where necessary and interactions variables are included. A correctly specified model is a model that not only missed out relevant predictors but also did not include redundant and extraneous predictors into itself. The estimated regression function from a correctly specified model is a one wherein The estimated slope coefficients BIs shall be unbiased estimates of the population regression function slope coefficients beta i's. Unbiased means with each estimated slope coefficient BI calculated from a random sample, the mean of the slope coefficients BIs calculated from every possible random sample out of the population equals the population regression function slope coefficient beta I. Similarly, the predicted value of y hat, for a given set of values of the predictor variables x1, x2, etc., xp, using the estimated regression function from a correctly specified model, shall be an unbiased estimate of the mean y value y bar from the population regression function for that set of values of predictor variables x1, x2, etc., xp. In other words, mean of y hat across all possible random samples at a given set of values of predictor variables x1, x2, etc., xp equals the mean y value y bar from the population regression function for that set of values of predictor variables. By extending that argument in a correctly specified model, the mean residual sum of squares, denoted by SE square, equals SSR divided by n minus p plus 1, is an unbiased estimate of the variance of error sigma square about the population regression function. Unbiased estimates of population regression functions, slope coefficients beta i's, mean value y bar, and error variance sigma square using a correctly specified model results in successfully validating the model's utility and more precisely predict the response variable y and or estimate the mean value of y when the model is deployed. An incorrectly specified model can be one wherein the model is underspecified, or model includes extraneous predictor variables, or model is overspecified. Underspecified model is a one in which one or more important predictor variables are missed out. Model with extraneous variables is one in which the predictors that have least or no influence on the response variable and no relationship with any other influential predictor variables are included. The overspecified model is a one in which one or more redundant predictor variables are included. We'll look into each one of these models and the consequences in detail. An underspecified model can be the worst among the incorrect models. An underspecified model results in biased slope estimates, which in turn results in consistently biased prediction values and mean value estimates. In other words, results in consistently over or underestimated values. In addition, the mean of SSR, SE square, often overestimates error variance sigma square, resulting in wider prediction and confidence intervals. A model with extraneous variables, though incorrect, results in unbiased estimates much like the correctly specified model, but with the following disadvantages. Since there are too many predictors, the degrees of freedom associated with SSR reduces, which results in higher SE square and thus higher confidence and prediction intervals. The mean of SSR SE square often overestimates the error variance sigma square, resulting in wider prediction and confidence intervals. Higher SE square and inflated number of predictors P result in lower value for the F statistic, which lowers the power of the hypothesis test. Meaning, in this particular case, the probability of failing to reject the null hypothesis, even when it is false, increases. In addition, the model becomes more complicated with increase in P, and interpreting the model becomes much more complex and harder to understand. An overspecified model results in unbiased estimates, like in the case of a correctly specified model. However, though a part of the model is correct, it has gone overboard by adding redundant predictor variables. Redundant variables, by the very name, are those whose influence on the response variable are accounted sufficiently by the predictor variables already included in the model. More often, these are the predictor variables that exhibit a high correlation with those predictor variables that are already included in the model. Adding redundant variables results in inflating the standard errors associated with the slope coefficients. Between the random samples, the slopes of each of the highly correlated predictor variables exhibit wider swings, resulting in wider or inflated standard errors for the slope coefficients. We will revisit this consequence when we discuss on multicollinearity a little later. A model with redundant variables, though is useful for predicting the response, should not be used to describe the effect of each of the redundant predictors' influence on the response. Like in the case of a model with extraneous variables, the model with redundant variables become more complex and difficult to interpret. Therefore, ideally speaking, model building exercise should result in a correctly specified model which is between an underspecified model and an overspecified model. However, one can make certain relaxations based on the goal of the exercise. When the goal of the exercise is to identify the individual predictors and their individual interactions with the response variable, then a correctly specified model becomes an obvious choice. On the other hand, if the aim is to predict or estimate the mean of the response variable, then the inclusion of redundant variables, that is introducing multicollinearity, is not a constraint. Therefore, the goal of the exercise decides the approach in the model building process. Let's now focus on the model building process that deals with the steps in arriving at a best suitable model. We discussed on this diagram as part of the lecture on model evaluation. Model building should involve in minimum the following steps. Identify and consider all the candidate predictors. Easier said than done, but this is a crucial step. Cannot afford to miss on identifying the candidate predictors. Don't worry about the transformations on some of the candidate predictors or inclusion of indicator variables at this stage. Use one among the following two variable selection procedures to arrive at a model that is neither underspecified nor overspecified. A. Stepwise regression. B. Best subsets regression. Fine-tune the model only where necessary by making appropriate transformations to selected candidate variables and adding interaction terms. Check the model behavior by examining the residuals. If the model is not satisfactory, iterate back and forth between formulating different regression models by trying out different transformations and or adding or removing the interaction terms until the residual behavior and the model in overall are satisfactory. The two variable selection procedures form the core in the model building exercise. Let's focus on them and learn them in detail. We will further discuss on these two methods in model building, namely stepwise regression and best subsets regression, that will assist us in arriving at the correct choice of predictors for the model. That brings us to the end of the lecture on understanding the correct and incorrect models and sequence of steps and methods in arriving at a correct model. In this lecture, we focus on the concepts behind the stepwise regression method for model building. We learn the steps in detail, we apply the steps using a real-world example, and finally add few cautions and points to remember before choosing to deploy the stepwise regression method for model building. In the nutshell, stepwise regression method involves adding or removing candidate predictors to the model one at a time, until the situation arises wherein we find no justifiable reasons to either add or remove any predictor to or from the model. The criterion to add or remove a predictor to or from the model is the partial F statistic along with its p-value, calculated for each of the predictors at every stage. Interestingly, there is a direct relationship between the partial F statistic and the t statistic for every predictor variable. Partial F statistic equals t statistic square. For example, For the infarcted area, partial F statistic, which is 32.75, equals T statistic square, which is 5.72 square. And so is the case for x2 and x3 as well. Therefore, as a criteria to add or remove a predictor to or from the model, the T statistic along with its p-value replaces the partial F statistic. Let's get into the details of the stepwise regression process. Having chosen the T statistic along with its p-value as the criteria to add or remove a predictor to or from the model, we also need to define two alpha values, that is significance levels, namely alpha to add and alpha to remove, to evaluate the criteria. Typical value normally assigned to these alpha values is alpha to add equals alpha to remove equals 0.15. Note, at 0.15, these alpha values are much higher than the 0.05 significance level assigned normally for the hypothesis test. Higher alpha values are assigned in order to allow some leniency in adding the candidate predictors and allow more tolerance before removing a predictor. Let's understand the steps involved in building a multiple regression model using stepwise regression. Step 1. Start with a model that does not include any candidate predictor. Create p different models by adding one candidate predictor in each and calculate the T statistic and associated p-value for the added candidate variable in each of the models. Is there at least one model wherein the T statistic has a p-value which is less than alpha to add? If no, stop the model exercise with no candidate predictors added. If yes, go to step 3. Step 3. Choose the model whose T statistic p-value is the least among the p different models. Let's assume it's the model with the predictor variable x1. Step 4. Create p-1 different models by adding one candidate predictor each from the remaining p-1 predictors to the model arrived at step 3 and calculate the T statistic and p-values for the candidate variables in each of the p-1 models. Is there at least one model wherein the T statistic p-value of the second predictor added is less than alpha to add? If no, stop the model building exercise with just the first predictor added to the model. If yes, go to step 5. Step 5. Choose the model in which the T statistic p-value of the second predictor added is the least among the p-1 different models. Let's assume it's the model with predictor variables x1 and x2. Step 6. Check if by adding x2 to the model, the T statistic p-value of the first predictor x1 has increased above the alpha to remove value. That is T statistic p-value of x1 greater than alpha to remove? If yes, remove x1 from the model, leaving the model with just one predictor, that is x2, and go to step 7. If no, go to step 7 directly. Let's assume this is the case, that is T statistic p-value of x1 is not greater than alpha to remove, and hence we go to step 7. Step 7. Repeat the just discussed sequence of steps as follows. Create newer models by adding a candidate predictor from the still not added list of predictors to the model. Choose the model that qualifies the alpha to add check. Remove the previously added predictors which fails the alpha to remove check, if any, and repeat these steps until there are no more candidate predictors that qualify or fail the alpha to add and alpha to remove checks. Finalize that model. Let's understand the stepwise regression method using an example. Sample data provided below helps in understanding how the composition in cement affects the heat generated in calories per gram during the hardening process. There are four candidate predictor variables and they are regressed on the response variable y as per stepwise regression methodology. To arrive at the significant candidate predictor variables that describe the variation in the response y in a most effective manner, satisfying the statistical requirements that we have learned that a multiple regression model need to comply with. Let's first begin with the matrix plot to visualize the relationship between the response and the predictor variables and between the predictor variables. You get to see a strong relationship between y and x2 and y and x4. It's therefore logical that we expect x2 or x4 or x2 and x4 to make their entry into the model. We also notice a strong relationship between x2 and x4. What impact does this relationship bring to the model? We'll get to see as we proceed with the model building process. Let's start with the stepwise regression process. To start with, we create four models, each with one predictor from x1, x2, x3 and x4. With alpha to enter alpha e equal to 0.15 and alpha to remove alpha r equal to 0.15, we get to see these tables showing the statistical quantities associated with each slope coefficient. The t-statistic p-values in all the four models are less than alpha e, which is 0.15. However, only models with x2 and x4 provide the lowest t-statistic p-values at 0.001. Since there is a tie on the t-statistic p-values at 0.001 between x2 and x4, we choose x4 over x2 because the absolute value of the t-statistic of x4 at 4.77 is greater than the absolute value of the t-statistic of x2 at 4.69. With x4 making entry into the model, we proceed to update the model by adding one predictor at a time from the list x1, x2, x3 of the left out predictors, thus resulting in creating three different two predictors models. Examination of the t-statistic p-values of the three models reveal that the model with x4 and x2 failed to qualify as the t-statistic p-value of x2 in this model is greater than 0.15. Between the remaining two models, we see a tie in the t-statistic p-values and therefore we choose the model with x4 and x1 since the absolute value of the t-statistic of x1 in the x4 x1 model is greater than the absolute value of the t-statistic of x3 in the x4 x3 model. Note, by adding x1 to the model, the t-statistic p-value of x4 remains lower than the alpha to remove, that is alpha r equals 0.15. Therefore, the predictor x4 is retained in the model. With x1 making entry into the model and x4 retaining its place in the model, we proceed to update the model by adding one predictor at a time from the list x2 and x3 of the left out predictors, resulting in creating two different three predictors models. Examining the t-statistic p-values of the two models, we choose the model with x4, x1 and x2 since the t-statistic p-value of x2 in the above model at 0.052 is less than the t-statistic p-value of x3 at 0.070. As the next step, we examine the t-statistic p-values of the already added predictors x4 and x1. We notice that the t-statistic p-value of x4 equal to 0.205, which is greater than alpha to remove, that is alpha r equals 0.15, while t-statistic p-value of x1 equals 0.000. Therefore, we drop x4 from the model, resulting in the model with only x1 and x2 as predictors. We continue to update the model, by this time adding one predictor at a time from the list x3 and x4 of the left out predictors. Note, we again attempt to add those predictors that we dropped. That's the way the procedure goes, resulting again in creating two different 3-predictor models. Examining the t-statistic p-values of x3 and x4 in the newly created models, we find that neither of the t-statistic p-values qualify the alpha to add criteria, as both t-statistic p-values are greater than 0.15. Therefore, we drop x3 and x4 from the model, and with no more candidate predictors qualifying the alpha to add criteria, we conclude the stepwise model building exercise by just fitting two predictors x1 and x2 to the model. In practice, arriving at the choice of predictors for the model using stepwise regression from the full set of candidate predictors is not so cumbersome or long. Software tools like Minitab provides the final result, but also capturing the snapshots of the predictors added to or removed from the model at each intermediate step. Here is the result provided by the Minitab with all the details at each step. Table in the top provides the details on the predictors added to or removed from the model at each step. The table at the bottom provides the details on the standard deviation of the residuals and various R-square measures at each step. Step 1 adds predictor x4 to the model. Standard deviation of the residuals R-square, adjusted R-square at step 1 are calculated and presented. Predicted R-square and malloc CP, which we will learn soon, is also calculated. Step 2 adds predictor x1 to the model that already has x4. Standard deviation R-square, adjusted R-square, predicted R-square and malloc CP are calculated for step 2. Step 3 adds predictor x2 to the model that already has x4 and x1. Standard deviation R-square, adjusted R-square, predicted R-square and malloc CP are calculated for step 3. Step 4 removes predictor x4 from the model since it fails the alpha to remove test. While x3 failing the alpha to add test, the model finalizes with predictors x4 and x1. Standard deviation R-square, adjusted R-square, predicted R-square and malloc CP are calculated for the final model. Note that R-square, adjusted R-square, predicted R-square values are lower in final step 4 than in the previous step 3, and the standard deviation of the residuals is higher in step 4 than in step 3. Still, we choose the model arrived in step 4 over that in step 3 because the stepwise regression model focuses on the t-statistic p-values as the qualifiers. Some cautions about the stepwise regression method. Does the stepwise regression method deliver the best or the most optimal model? No, it delivers a single good model which need not be the best or the most optimal. Stepwise regression method does not take into account the domain knowledge required in ensuring the right composition of the predictors. The researcher's intervention may be required to force in the important predictors, if any. The order in which the predictors are added to the model is not meant for any rigorous interpretation. The stepwise regression method involves a series of t-tests. Since every t-test in every step is associated with a possible type 1 or type 2 error, the decision made at the end of each step may not be the precise one as against the intent, thus leading to an incorrect model. We might have wrongly included unimportant predictors or dropped the important ones. That brings us to the end of the discussion on the stepwise regression method. And in the next lecture, we shift our focus onto best subsets method. That brings us to the end of the lectures on multiple linear regression, model building and stepwise regression method. See you back soon with the next lectures on this topic on multiple linear regression models. Bye for now.